This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right, we'll get underway. Okay, where we left off last week was we were still looking at embedded processes. And I'm going to spend just a little bit of time on talking about parallelism. I hate that word, but operating in parallel. Why? Because it ties in nicely with the lecture, the real lecture for today, which is going to be on memory architectures. And if you think you know everything about how RAM works on a PC, right, it's very different for an embedded system, how memory works, okay? And it's messy and a whole area unto itself. So last lecture we looked at the difference between concurrency and parallelism. Parallelism is where you have a program that physically works at the same time, but concurrency is when it looks like it happens at the same time, but it doesn't necessarily happen at the same time. And so there are multiple ways of doing parallel processing. Down the bottom here, multi-core is the simplest way to describe parallelism, but then there are tricky ways of doing it with using instruction-level parallelism. I spoke a bit about CISC instruction sets. DSPs use CISC instructions, very complex instructions almost from a high level that don't give you access to individual units. And so that gives you a level of parallelism because, say, for instance, you can run a fast Fourier transform operation and the hardware knows how to do that in parallel because it knows it has multiple functional units that don't interfere with each other. But CISC instruction sets are difficult to deal with, and indeed for most embedded processors, particularly when we look at microprocessors as opposed to microcontrollers, as opposed to DSPs, CISC instruction sets don't exist. Okay, so how else can you get parallelism out of a processor? Another way of doing it is using what's called subword parallelism. And where did this originate? It came in the 90s. Intel was a big pusher of this. And the idea was that if processors were getting wider and wider in terms of the arguments that they can take. So, for instance, you might have a 32-bit processor in the late 90s. Okay, well, you would have a 32-bit processor. 64-bit processors were, crazily expensive and reserved for servers. And so what the problem was as the internet was developing, you had a lot of low bandwidth multimedia stuff. So you had 32-bit processors, great, they can operate on 32-bit wide arguments and do fantastic calculations, but the media that they were doing the calculations on was perhaps 8-bit media. So for instance, your images were 8-bit RGB images, where there would be an 8-bit number for each of the RGB colours. So there's the problem is you've got a big 32-bit processor and you're going to have to be doing 8-bit operations with it. Okay, so that seemed very wasteful. So the idea was you took instructions and you allowed them to operate on multiple chunks of 8 bits at a time. So for instance, the MMX technology is a great example of this. It was the multimedia extensions technology. And the idea is that there were some special registers dedicated to implementing this technology. And what you had was you had, say, a 64-bit register. Okay, so you could stack two 32-bit numbers together, and it was only a 32-bit processor that could deal with that. This is the chunkiest pen in the world. What's going on here? Okay, 32-bit, or it would be considered two 32-bit. These are registers. So it had these dedicated MM registers. And these were called multimedia registers. So, and it was in what was called a packed format. So you had 64 bits, two 32 bits, 4 16 bits, and you can guess the rest. There was also 8 16-bit registers. So the idea was these were special registers that were kind of 64 bits wide, but they were really segmented into like, you know, either 16-bit blocks, 32-bit blocks, a 64 and 8-bit block. And what happened was the processor could operate on these individually. So you had these special MM registers plus special multimedia extension instructions. And it was really clever. What those instructions could do was look at one of those special multimedia registers, take, say, for instance, two 16-bit numbers out of there, and subdivide the ALU in order to do calculations on the two 16-bit numbers independently. Okay? So if there was addition or multiplication going on, you would stop carries from occurring and all that sort of stuff from poisoning the other half of the calculation. And it had a great advantage when you looked at 8-bit processing. So for very simple 8-bit multimedia stuff, you would have 8-bit numbers in there. So you could do heck of a lot of processing on those things. But it needed special instructions to tell the ALU to command the hardware in a particular way so it didn't upset things. So this is an example of really a vector processor. It supported this subword parallelism. Okay, so your instruction words could operate on sections of registers. And it was huge. Intel, it sped up processes unbelievably. I was there at the time, right? Things just immediately sped up, particularly for streaming data and that sort of stuff. So much so that AMD came along and copied it, and then copied the idea of it, and then took Intel to court and tried to use the MMX designator, like to describe the technology, and it was a big court battle and settlements and all that sort of stuff. Okay, so that's one way of getting parallelism, right? By special instructions and dividing registers into smaller chunks. Another way of doing it is using what's called a superscalar processor. Now, superscalar processors sound fantastic. They are fantastic, but they're very, very uncommon in embedded systems. Okay, what is a superscalar processor? It's hardware that can decide to send out multiple instructions to different hardware units at the same time. It's extremely complicated. Okay? From the outside, watching a program run and not knowing what the process is doing, it just looks like There's a program running. But internally, the processor knows its own functional units, you know, things like counters and adder blocks and all that sort of stuff. It can see instructions and sort of stack them up and send them out at the same time to units that don't interfere with each other. Okay? But it's done dynamically. Okay, so the processor can schedule these things by dispatching them at times to all of the different functional units. And that's awesome. That's a great use of resources. You're doing multiple things at once that don't interfere. But there's big, big problems. In embedded systems, we are super concerned with execution time, okay, and reliability. And if you think about a processor that's dynamically sending things out to different parts of, you know, sub-blocks of its architecture at any one time, and then you throw on some extra stuff like interrupts happening where it's in the middle of doing something and has to go and do something else. If you think about threading, we won't go into threading, but having multiple things happening concurrently, seemingly concurrently, the timing essentially becomes totally unpredictable. Even worse, you may not ever be able to repeat something ever again. So you run something, you get some known timing on doing something, right? You know when it's going to access the I/O part, when it's going to access the memory, when it's going to do an ADC conversion. You run it again, and all those times are different. So while it's okay probably for highly specialised tasks where you know exactly what's going to happen and all that sort of stuff, in general for embedded system superscalar processors are not great because they're too dynamic, right? They're doing things on the fly. But it's interesting. It's an architecture that's out there. What's more common is the use of what's called VLIW, very large instruction words. And this is a sort of a method of doing superscalar stuff, but it's where the programmer or the compiler decides when to use the functional units. So instead of writing a program and letting this magic hardware allocate things and dispatch things, you have the control over that. Okay, so you've still got multiple units that can do functions at the same time in parallel, but the instructions themselves say what to do. For instance, you might have a single instruction that would be segmented into FU1, FU2. Yeah. Great acronym there, but and we'll go up to FU4. So what happens is that's one instruction word, but inside there you have 4 sub-instructions that basically control 4 separate functional units that don't interfere with each other. Okay? So who's writing these instructions? Well, the programmer knows the architecture, knows the units that can be programmed at the same time, and therefore writes the instructions like that. Additionally, you could have a compiler that could come along and take some C code and then convert that into operations that run in parallel like that. Okay? Now, the beauty about that is a compiler is a repeatable thing generally. Right, you compile the code, you put in your optimization parameters, out comes a binary, and you compile the code again with the same options, and out comes the binary, same binary. So it's always going to run the same way. There's none of this dynamic, weird stuff happening on the fly. So timing is very easy to work out what's going on here. When a task will complete, how often the units will be used, all that sort of stuff. Okay, so VLIW is very common in embedded systems. Okay, so how else do you get parallelism? And this is a pretty basic one. Why is it obvious? Because it's ubiquitous now in general purpose computing. Use more than one core. Okay, so when we talk about general purpose computers with quad core, hex core, whatever, octa-core, right? These are independent CPUs, largely independent, I'll say, that operate on the same die, right, and all in the one chip. For embedded systems, you tend to get, and I'll say that for general purpose computers, these are heterogeneous processors. Okay, Core i7, quad Core i7, has all four of the same damn things sitting there. Okay, exactly the same instruction sets, same architecture, whatever. But with embedded systems, you tend to have this mix and match approach. That you have dedicated processors that do real-time stuff, generally safety critical things, and then you might have another processor that can be user programmable for user applications. Okay? Now, a great example of that is going to be, I'll just flick it across here, is going to be the processor that you're going to use for the workshop. So the brains of running the robot is going to be this thing here. It's a National Instruments myRIO 1900. And it's in the best box in the world, right? You can't break it. Very hard to wreck things on it. But right in the middle here, it's very hard to see, but I don't even know if it's upside down as well, is a Xilinx Zynq, Z-Y-N-Q. And that is a hybrid sort of embedded processor. It has an ARM Cortex core on there that can run code and stuff, as we'll see a little bit about how the memory of that's laid out next lecture. But it also has an FPGA in there as well, all in the same, chip. And the FPGA can be programmed with its own personality. Okay, and that does very low-level stuff, hardware stuff. If you think about what an FPGA does, it's gates and things connected, registers, D flip-flops, that sort of stuff. There's no operating system on there. Okay, so that does all the safety critical or real-time stuff where you need to do, say, ADC conversions, PWM control of motors, that sort of stuff, right? Real low-level hardware stuff. You then, via an interface, talk to the actual processor part, which you program. Okay? So this is where things are at now, right? Where we get these hybrid sort of systems. Very different to your Core i7, quad core, four of the same damn things all in the one chip, right? Boring. These things are much more prevalent in embedded systems. Okay, so my example would be, say, mobile phones, because radio and speech processing are hard real-time functions. There's a lot of crunching going on there. If you've done some signal processing and you know a bit about how signals are decoded and demodulated and all that, there's a lot of stuff that has to happen with minimal delay. Okay? All the other user crap that goes on, right, apps and all that sort of stuff, that doesn't matter if those things are delayed a bit, but those core functionalities have to be done in real time. And the user application should not be able to interfere with them. Think of safety critical stuff, right? You don't want to use an app being able to stall things on the real-time system side of stuff. Otherwise, bad things can happen. Okay. Should I mention it now? I could mention it a bit now. So even multi-core processors in your stock standard Intel i7 core, quad core, are not that independent. They typically share caches. We'll talk about cache a little bit later on. But those processors access a common cache. And processors that hit the cache could also cause collisions with other processors hitting the cache as well. So they're not quite independent as such. You can actually have one processor affecting the other processor via the memory. Okay, so it's not very simple. All right, even though they're heterogeneous, they're all the same processors. And as I mentioned before, FPGAs are commonly used in embedded processors alongside maybe a general purpose, like an ARM processor or something like that. And you can even implement soft cores on them as well. You can implement your own CPUs on FPGAs, okay? And indeed, you'll be using the microblaze functionality, personality, I should say, on the Zinc platform or the Zinc architecture in the workshops, okay? The best bit about soft cores is that they can be highly specialised to the application that you want, right? An off-the-shelf processor has to be a bit of everything, whereas you can do an FPGA that's very, very tight, custom, timing very predictable, all that sort of stuff, particularly for real-time tasks. Okay, so hopefully that's given you a bit of a taste of what's out there in terms of embedded processors. I will talk a little bit more. We're going to give some examples again when we talk about memory architectures now. So I'm just going to flip across to the next slide set. Hopefully. Yes, you can load. All right. And now we're going to look at how memory, which is, well, we need to store things, is interfaced to these processes. And it's not a trivial task. It's not just go and get a stick of RAM and go and shove it in some slots in a DIMM slot in a computer and you're done. Or overclock some RAM and try and get it to smoke or something, right, catch fire. Okay, so where is this going on here? Okay. So the reference for this is chapter 9 of the text here. So what does memory do? I'm pretty sure you understand that memory stores stuff, right? And it's used as a communication mechanism as well. Think of it as a common area where things can be put and other things can then access it. So it's like it's a comms region, if you like. And the communication is done with sensors and actuators, okay, either inputs or outputs. Think of those as inputs or outputs. You are much more constrained with memory in an embedded system than you are with a general purpose computer. Indeed, general purpose computers with 16 gig of RAM and virtually unlimited virtual memory, no one cares about running out of memory space, right? You have complex operating systems which can handle all of the memory mapping and all that sort of stuff. You don't even need to think about it. For embedded systems, you have to, not only in terms of the size, the power, but also the reliability. Now, you may have been tinkering along, writing C code and stuff like that, not thinking about what happens in the memory space. You typically don't have to. When you compile it, you let the compiler choose which architecture you're compiling from, and it handles it all. But it is very, very important for programmers to know what the constraints of the embedded system are. In particular, you know, I've had to do it myself. I've had to write assembly subroutines in assembler in order to get down into the nitty-gritty part of using the memory. So we're going to cover things that you might think would be basic. SRAM versus DRAM. That's not as simple as it seems. How memory is mapped in the system. So you're writing a piece of C code. When you're instantiating variables, where do they live in the memory space and how are they being accessed? And there's a couple of ways of doing it. Statically allocated and also dynamically. And dynamically involves stacks and heaps. Okay? And stacks are essential for embedded systems. Okay? And knowing what's happening with the stacks. I'm then going to talk a bit about how C works, memory model of C. Why C? You should have all done something like, what's that subject called again? Engineering computation. So you've had exposure to C. C is a great language because unlike MATLAB, unlike Java, all that stuff, you have virtual direct access to hardware. Okay, you can actually get right in there and play with pointers and stuff like that, which you don't get to do on sort of higher level languages. Okay, all that stuff's hidden from you for good reason. And that's what I said before, right? These issues, all of these issues about memory are much, much, much more important issues than are in general purpose computing. As I said, you're a hacker programmer on a computer writing some stuff in Java. You don't care about the memory space. You really don't. You know, it just has memory and you just use it, right? And you let all the routines handle things. Okay, let's get into it. I'll give you a bit of a fly through history very, very quickly. EPROMs were the first sorts of types of programmable memory out there. By programming, you programmed it electrically, so that's the E part. Well, erasable was the E part, but you still programmed electrically. And how did you wipe these things? They had a window on the top of them. So that is the actual internal part of the chip. It's not a cutaway. That is actual visible part of the chip. There was a window on the top. It wasn't made of glass. It was made of quartz. And what you did was you put it in an oven. Now, not your regular sort of high temperature oven, but an oven that baked it with UV light and it erased it. So it was pretty hard to be reprogramming these. You need a specialised oven that had safety features on it so it didn't blind people with UV light and all that. They give you a tan, all of that sort of stuff. Then along came EEPROM. So it was much simpler then to electrically erase it. And that only happened in the late 70s, and Intel were the big leaders here. Then along came flash memory. Flash memory is different to EEPROM. It's a different architecture. We won't get into the nitty-gritty of how it's all laid out internally. We're going to be dealing with this from sort of a level up, talking about the memory from a higher level. And flash memory has to be erased a block at a time due to the way it's structurally organised. You can't just erase one, tiny bit at a time or even a byte at a time. You have to do it on a blockwise basis. But the big thing here is that you only have about something like 100,000 program erase cycles, write-rewrite cycles. And after that, it becomes useless. All right? So that means that you have to be very mindful of where the flash memory is being used. It also means that there are controllers for the flash memory that are very complicated. So what they try and do is they intercept writes to a device and they try and sort of steer it to locations on the disk where it spreads out the load. So you're not punching the same point 100,000 times because that won't last long, right? That section of the flash memory will be wrecked, right? It'll degrade sufficiently you can't use it. And so that's what SSD controllers do essentially, right? Trim controllers, that sort of stuff. They sit there and they try and work out where to put stuff. So even in SSDs, like in here, there's a little controller that's trying to work out the best place to put stuff. It has a table of where the locations have been written to. And as you get more and more out of space, it's not a good idea to operate an SSD with not much space left, and I'm guilty of that on this machine, because the amount of available areas where the controller can write to is quite limited, and you'll get a wear out very quickly if you only have a small area that can be written to. Okay, so I kind of think of it, the load balancer there of writing, it's like instead of having sections of the memory fail at different times because they're being written to, you kind of spread it out so the whole memory dies all at once, right? Because you've tried to balance it out over time. Okay, disk drives, they're not well suited for embedded systems. We're talking mechanical. As soon as you have mechanical disks, you have anything mechanical has problems. Okay, movement, that sort of stuff. So they're hardly used at all. Size is also an issue with mechanical disk drives, so we don't even talk about that. So that's non-volatile memory. So what about volatile memory? And that's what we're going to focus a lot on today. Broadly speaking, there's two types of volatile memory, SRAM and DRAM. I'm sure you've heard those acronyms before. There's advantages of both, and there are disadvantages of both, right? So SRAM is wonderful because it's very, very predictable. Does anyone know what SRAM is made up of? If you went and zoomed in on some SRAM, what functional units it's made up of? Capacitor? No, that's DRAM. So SRAM uses latches, basically. Little SR latches in there, right? To store one bit at a time. It's very fast. It's deterministic because you can get things like setup and hold times on latches. There's known processing time on those. But it's more power hungry and it's less dense. To implement a latch needs about 6 transistors to do that. Okay, so it's a bit of space on the chip. DRAM is dynamic, and I'll explain why the word dynamic is there in a minute, but it's slower than SRAM. It's implemented as a capacitor. Okay, so it will have one capacitor and one transistor per bit of memory. So what that means is you can get much higher capacity, right? Instead of 6 transistors, you just have a capacitor that's storing the bit, and also a transistor on there to drive it. But there are inherent problems with DRAM. DRAM, great, you can get much more stuff crammed in on the one area, but then you have problems. The problem is, well, there's 2 problems here. I'll do the bottom one first. What happens with capacitors? No matter what size they are, they leak over time. And indeed, these capacitors leak. So what happens is you need to implement a periodic refresh. There needs to be a controller in there that actually reads the RAM back, reads the RAM into a temporary buffer, and writes it back to it, independent of what the user application's doing. The little controller there is doing these refreshes. Why? Because otherwise, if you left the capacitors for too long, they would actually just discharge and lose the values in there. And you get crap in there, basically. So you need a controller that does that. And due to the way that the RAM is organised, the access time is very hard to predict. It depends on the sequence of addresses you have accessed. If you access them as a block, or if you access them in different banks. Okay, sometimes, depending on the architecture, you can't have accesses to 2 accesses to the same bank at the same time, or close to each other. So where this is typically used is for main memory, where you can just dump a whole bunch of stuff where the timing is not super critical. Now, how do you, because this is volatile memory, how do you actually make it start in a known state? If you turn on your wonderful embedded system, what's in the memory? Rubbish is the answer. You cannot predict what's in the memory when you power it on. So typically what happens is there's a little mini bootloader in the system. Okay, and if you've ever done any firmware hacking of devices or something like this, it's typically that bootloader that you program. And it has disastrous effects if you get it wrong, right? You get a brick, basically. So this bootloader, what it does is when you power up the system, the bootloader's typically read-only, a little read-only bit of chip. Sometimes it can be reprogrammed with firmware upgrades. And what it does is it basically writes into the memory space and writes what needs to be in there immediately upon power up. Okay? It's a very simple mechanism. It'll set the program counter to go to a certain location and feed in any, say, initialized variables and things like that into the memory space. Okay, so the bootloader basically handles that. When you turn it off, well, obviously you lose what's in there. You turn it on again, the bootloader has to do everything again. So we're going to talk a little bit about, well, in chapter 16 in the book here, later on in the course, we're going to talk a bit more about the timing issues that are involved with some of this stuff here and making sure that it's predictable and it's also repeatable, right? An embedded system has stability in that sense. All right, so just to give you a taste of what a typical processor might have on it. I don't have my pointer here, but there's this massive one here. Ugh. Whoa. It's old school, look at this. Andrew would be jealous, wouldn't he? Now, so this is an M3, an ARM architecture. It's quite complicated. There's the guts of the processor. You've got two sort of big sections there. There's some fancy stuff going on there, like, you know, the I/O-ish sort of stuff, power supply, all that. But that's the brains of the processor. And there's two big blocks up and down. The top block is the flash memory. That's where the program's stored that runs. And down the bottom is a bunch of DRAM down the bottom for doing some, on-the-fly calculations. The thing about flash is that it has the same, so the flash is up here. Flash has the same sort of silicon layout as the micro processor itself. So that's why flash is very amenable to getting it onto a chip and being an all-in-one thing. Okay? So you can have a nice look at that picture there. This is the memory mapping of that processor. It's a fancy processor. It is a 32-bit processor. So it's a 32-bit processor, which means that it has an addressable space of 2 to the 32. And that's about 4 gigabytes, if you want to think of it in bytes, about 4 gig. This is, if you want to design for this architecture, this is how it's laid out. This is the, this is the physical part of the memory, and this is what's called the logical. So physical address and logical address. Physical means where it really is, and logical is where it looks like from a program's perspective. And that's just a number, a hexadecimal number, where it lives. Now, this is the architecture for this processor, which basically limits the size of things. Okay, so you go and buy an ARM Cortex M3, it doesn't mean it has 4 gig of onboard memory. Okay, this is just the limitations of the architecture. You can have maximum half a gig of program memory, maximum 1 gig of DRAM. There'll be different architectures where you can buy ones that have, you know, smaller spaces here, not the whole space is used, but it's segmented. So why do you do segmentation like this? When you compile a C program and you compile it for an ARM Cortex M3, the compiler knows that there are areas that you shouldn't be accessing, right? Perhaps in the code. Okay, it knows that these boundaries exist. For instance, you shouldn't be writing into the program flash memory because you're overriding the program. Okay, so there'll be restrictions on that. Compiler would pick that up and go, hey, you're writing into the flash memory. Likewise, there are also restricted areas. A private peripheral bus, what on earth is that? That's perhaps reserved for things like debugging. Wow, this is it's loose or something. Debug, so that's like a debug interface. That's how you access the debug interface. And you have DRAM, SRAM, memory mapped registers. So peripherals here might be things like ADCs and things like that. Okay, so you write to those locations, you actually physically be controlling an ADC somewhere, or reading from it, writing or reading from it. Now, this is great having this architecture laid out because not only can the compiler pick it up, but if there's an OS on the top of this, there's an OS that's sitting there running, right? Running your little program, it can also restrict accesses into the other spaces. It knows what its layout is and says, hey, you can't write to that location because that's a protected area, all right? And you might need to go into kernel mode to start mucking around with stuff in there. So that's a high-end embedded processor. What about down at the simple level, the bare bones simple level? Who's heard of AVR before? AVR micros? Wow, one person? Yeah. Okay. What's AVR? It made the guys pretty rich. It's an 8-bit chip, came out at the right time when embedded stuff was really taking off. Developed by Atmel. It was one of the first ones to use flash memory and on board for program storage, an all-in-one micro. It has what's called a modified Harvard architecture, and you can read a little bit of Harvard architecture, but it essentially separates the program and data into separate spaces, right? If you don't have a Harvard architecture, you can have the memory space is just a bit all over the shop. There's sometimes instructions, sometimes data. Okay, this segregates it. There are the two guys that came up with the AVR micro and the instruction set for it. If you want to know where AVR came from, it came from their initials, right? Alf, Egel, and Vegard. But funnily enough, Atmel that bought the technology have never actually said what AVR stands for, although it's damn obvious. I don't know why. They just never say what it stands for, but it's their names. Okay, so Arduinos. Surely we've heard of Arduinos. Arduinos are a massive use of AVRs. Let me just talk about AVRs in general. If you think AVRs are these niche little things that just, you tinker with at university and you never see again, I'll give you a rough stat. There's somewhere between 1 and 2 orders of magnitude, so 10 to 100 times AVRs out there than there are general purpose Intel processors. Think about that. For all the computers that you can think, most are Intel, think of all the computers that are out there, there's probably 10 to 100 times that in terms of AVRs. So there's a massive industry out there, but also legacy products. Think about it. Controllers in cars, controllers in dishwashers, toasters, coffee machines, whatever that has some sort of control and has probably got an AVR architecture in there. So Arduino is an example. So for instance, this is an ATmega 328. It's a 28-pin DIP. What does DIP mean? Dual inline package, if you haven't heard of that before. Beautiful thing about these is they are what I call, is there an acronym for it? TFR maybe, something like that. Try it, fry it, and then replace it. That's basically how you play with these things, right? They're little practice boards. Because it's a dual inline package, you can remove it. So you can try something, if it fries, you just pull it off and go and get another one, pop it on. They're about down to like 30 cents each for some of these cheap ones. So they're essentially a throwaway item, which is amazing. Okay, so that's at the extreme end. This is bare bones. There's no OS on this, which is great because you have full control over the hardware, but it's scary because you can do some bad things and some dumb things, right? Particularly if something like this is a safety critical item. Well, I'll show you some coding examples in a minute where things that don't look obvious can get out of hand and maybe cause a system failure, and that means disaster for something. Inside, if you've ever seen the iRobot vacuum cleaner, so it's one of those little robot vacuum cleaners, the iRobot brand. Inside one of their models, they had an ATmega 168 inside there. Indeed, this is the actual main board out of the unit, and there is the ATmega 168. It's not a huge chip. It's an 8-bit microcontroller. That's all it is. It has some peripheral stuff on there, which I'll show you in a minute. It has 16-bit addresses. So it has a data bus here that is only 8 bits wide, but the addressable space of the memory is 16 bits. So I'll flip the slide. So it means that there's 16 kilobytes of flash memory that's accessible, basically, of the memory space that's available. And the memory is laid out like this. If you look down the bottom left here, that's how the memory space is laid out. It's all accessible. You've got 32 basic registers at the low end of the memory space. On top of that, you've got 64 I/O registers for doing, your various I/O bits and pieces. And then there's an internal SRAM that fills up the rest of the space. Oh, sorry, external I/O registers. Then you've got a bunch of SRAM that fills up the remaining space there. It's a micro, so it also has all of these other bits and pieces on here. It's got some timers. You need timers for doing something when you're cleaning the house, right? 6 PWM channels. You're driving motors. PWM's a good thing to use that. Got an ADC serial interface doing things like firmware upgrades and stuff like that. You can plug into it and do all that stuff. Okay, so that's what its architecture looks like. And this is a very standard, this is your standard AVR type architecture. Okay, the thing is about this is that even though it's only a 16-bit data bus here, you can still do more complex operations, right? The ALU is a 32-bit ALU, so you can actually do multiple things on 8-bit chunks at a time with this particular micro here. All right, we're going to actually look at this architecture for some examples, looking at what happens when you write some C code, where the stuff lives in the memory space. It's really interesting. Okay. It's very basic, once again. With such a small amount of flash memory, it means you cannot be writing fancy Java programs, right? Java is rubbish. It's a terrible language, right? Because it's super inefficient. It's too high level. For embedded systems, it is, okay? For embedded systems, you're going to be writing stuff in assembler or C for this because you ain't got much space and you don't even have an operating system on top of it. This is bare metal, so it's dangerous. Okay, so when you're coding, you don't have to write in assembler. You can write in C, right? One step above assembler. Don't put you through the torture of assembler. So it's important when you write the code that you know how the memory is laid out. Otherwise, you're going to end up with some problems. And we're going to look at how the memory is laid out. Firstly, with statically allocated memory. Typically in C, you're told not to do this, not to have global variables, not to have static variables. Sure, that's the computer scientist's point of view. When it comes to embedded systems, it's actually quite useful sometimes to have static variables because you know where they live in the memory space. And then the two different types of dynamic memory arrangement called stack and heap. There's a knocking sound. Okay, so let's have a look. You should be fairly familiar with C. So what I want to show you is some very trivial code and how it maps into a memory space. Wow, this is the simplest piece of code in the world. Function, a variable is declared outside the main function. It's an integer and it's assigned a particular value. So if you remember how chars work, this is basically an 8-bit quantity. Okay, ASCII. So it's an ASCII character, so it will use an 8-bit. It might be padded with a 0 or something, but it's 8-bit quantity. So it needs 8 bits to store that char. So what this little program does is, in the hardware, well, when the compiler compiles it, it actually chooses statically the address where X lives. So it'll pick a piece of the SRAM memory and go, okay, X, you're going to live in that slot there. And that memory X, in C, you know that X is now accessible, right, via other functions or procedures. Likewise, it's just a variable sitting in the memory space. So any other procedure can actually go and read that variable as well. The variable's lifetime is the duration of the program execution. So here's a really interesting question. If you wrote that code, how do you find where X lives? What memory location does x end up at? How would you work it out? Any ideas? Could you add a bit of code to this to work out where it is? Printf or something, yeah? Yep. Okay. That's a very good answer, right? You could write a printf statement or something to show where it is. Problem is, with an embedded system, you may not even have a screen, so printf doesn't exist, right? Or even you might even have a debug console. What you would have to do is essentially pull apart what the compiler's come out with, get the binary, and disassemble it to work out where it's mapped x to. It's pretty crazy, right? You have to go and dig right in there to find out where it is. What about if we did something like this? So another function, but this time we declare the variable x as a static char and pull it inside the function. Guess what? There's really not much difference. The only difference is that that variable now has this limited scope. It means that a compiler now will know if you try and call x outside of this function, it has a whinge about it, right? Which is good from the compiler catching mistakes perspective. But in terms of the hardware, essentially, nothing's different. It reserves a slot of memory somewhere for x, and x stays there for the whole life of the program, right? Just sits there, okay? All right. We are grossly running out of time. So next lecture, we're going to look at the stack, which is a implementation of dynamic memory here. And there's an animation where it grows and it shrinks over time. And this is where all your most of your variables will live and can be overwritten and such like that in the program. Okay? Then we have some questions on C code. And I expect you to have a look at these slides and try and have a go at these questions, because we'll write the answers out next lecture. Okay? We'll have to leave it there for today.